So yeah, today I'm going to talk about blockchain for AI. So this is how blockchain or distributed ledger technology is really the kind of uh, better description, I would say, for it, and the sort of alternative description for blockchain, and how that can support AI through a shared and trusted data model. So, as Edward mentioned there, both blockchain and AI are currently hot topics in technology. They're sort of buzzwords, but they're not really usually thought of as being very relevant to each other. Now, someone could say, well, you're taking these two kind of popular topics that we read a lot about in kind of tech news and even in kind of mainstream media now, and sort of just finding some way to sort of bring these together for a sort of more interesting discussion, or kind of getting some kind of new interest out of it. But there's actually a very good reason, what I'm going to go into now, why blockchain and AI are relevant to each other, and how blockchain can actually support and solve some of the challenges, at least, and some of the top challenges in deployment of AI solutions. So an overview today. So I'm going to firstly talk about some of the key challenges of deploying AI solutions. I'm going to talk about how blockchain and distributed ledger technology, DLT, enables trust and validation of shared data. I'm going to give an example then of a project that we're working on with a couple of industry partners on blockchain for shared trusted data models for supporting AI in supply chains. And then I'm going to talk about some limitations of blockchain technology, why it isn't a kind of solution for all of the challenges for that AI have, of course. So firstly, and these are some of the challenges in AI adoption that continually come up. And firstly, these are not things from necessarily a technical perspective that are coming out from what we see in CeADAR. This is from companies and respondents, and there's 3 surveys here that I've provided some results from. These are 3 different surveys of industry professionals of companies working with AI, asking them what are their challenges in AI adoption. And what we can see is there's a kind of consistent theme here. So some of the top reasons, they're all related to data or data quality. So we see in the O'Reilly report on the left here, that the second highest reason, at nearly 19% of respondents said that lack of data or data quality issues is a key challenge that they have, or that their organizations have. We see in the report from below here that data cleansing, data labeling, data augmentation, these are by far, again, the largest chunk of challenges here. And we also have data aggregation and data identification. So again, this is all related to these challenges with the data that powers these AI solutions. Again, on the Kaggle survey on the right-hand side, we see by far the top one here is dirty data. So this is data that's in formats that's difficult to process, or there's incorrectness in the underlying data as well. And we see it's unavailable and difficult to access there as well. So I think the overall result from this then is that we can see that a key challenge is really the data that AI, that powers AI, that AI relies on. And this is what organizations are finding when they want to deploy AI solutions. So we can look at some of these just in a little bit more detail. This is really showing the sort of the background for the challenges in AI, and I will go on later to talk about how blockchain or distributed ledger technology can approach these. But first, the problems themselves. So as we all know, that the quantity is a huge concern. So machine learning algorithms can require a lot of training data. And this was even the case, maybe a good 5-10 years ago, when we had more traditional statistical based machine learning algorithms. They still required a lot of data to train the models. But as we've seen advances in deep learning and deep neural networks, the amount of training data to build these networks has just increased and increased. These algorithms, they can provide highly accurate predictions, highly accurate results, amazing achievements really. But that's as added an expense of really requiring huge amounts of data to be able to train them efficiently. So as we see, some of the famous kind of open baseline or baseline data sets. So ImageNet, which is a classic image recognition data set that's used across the board from researchers and companies to test different image object recognition approaches, predominantly using deep learning in recent years. It now has 14 million labeled images. Google's open images data set, that's 9 million images. And if we look at other kinds of data, so audio set, it's clips of audio data for training AI models to recognize speech, for example. There's nearly 6,000 hours. And if you were to play those audio clips back to back, starting now, you'd be still playing them into December. So that's the amount of data that you need to train these kind of models. And what we see on the right here is a graph of some work that we did in CeADAR a few years ago, where we compared some more traditional machine learning algorithms, so k-nearest neighbor and reinforcement learning, with CNN there, which is convolutional neural networks, a deep learning approach. And we see on the y-axis is the accuracy percent. So obviously higher accuracy is better. And along the x-axis, we see increasing training set size, so increasing training samples. Now what you see is the more traditional algorithms, even at small training set sizes, they have a reasonable accuracy to begin with. And as we increase the training set size, the accuracy of these kind of traditional machine learning approaches, it does improve, but it tends to plateau off as we get really large training set sizes. If we look then at convolutional neural networks, a deep learning technique, as we increase the training set size, well, firstly, to begin with, at low volumes of data, we get really poor results relative to the traditional techniques. But as we increase the amount of data, the convolutional neural network model improves and improves, and it can then surpass the traditional approaches as we provide more data. And I mean, we were using a data set that sort of ran out at 60,000 image examples here, but as you increase that, you expect that the deep learning approaches continue to improve in their accuracy. So this just shows that data quantity is of a huge important aspect and is really a blocker to the deployment of a lot of AI techniques. A second challenge that we saw from above is accessibility. So data, it's often siloed across different departments, different databases within an organization, or even across multiple organizations. And I bring in what I'll talk about later in the context of a supply chain here, where you have multiple organizations maybe that need to coordinate closely with each other, but they all own their own data and they don't necessarily want to share that data. And even if sharing was possible, it might be in different types of systems, in different formats. So just pulling that data together and aggregating that across these different silos becomes a huge problem. Within organizations themselves, organizations might take on, through acquisitions and so on, they might take in different companies with their own systems. So large organizations typically have a lot of legacy systems. The data spread across these is hugely valuable, hugely important. And for AI solutions that really need access to these different pots of data, these different silos of data, there's huge potential there. But just pulling that data and getting access from the AI models to this data is a real challenge and is a real blocker to actually deploying those kinds of solutions. Data is often also guarded and protected because for a lot of industries, a lot of companies, the data that they have is the key value. It's competitive advantage, the data that they have on their customers, on their on whatever area of industry they're working in. They want to protect this. They don't want to share this. They don't want to necessarily open this up across, even within an organization. It's valuable. And it can also be a liability. So with GDPR as well, there's a lot of, there's a hesitancy maybe to share data these days, especially if it relates to customers, if there's personally identifiable information in this. So this accessibility then again hinders the application of AI solutions, and talking here predominantly about machine learning solutions, which is sort of the key paradigm of AI currently. Then we're going to introduce now, moving on to blockchain or distributed ledger technology. So we've been talking about data quantity, we've been talking about quality, excuse me, which I think I skipped over this slide. So the third aspect is data quality that we mentioned here. So training many of these types of AI models requires properly annotated training data. So we've discussed about volume of data and accessibility to data, but just having large amounts of data isn't what you need and won't lead to good AI solutions. You need that to be annotated. So this involves cleaning the data, correcting incorrect data, and formatting this. And it's all very manually intensive. Usually this has to be labeled by humans initially. And also this poor quality data can lead to poor quality AI solutions. So one example from a number of years ago now was a chatbot from Microsoft called Tay. That was trained on a data set that was scraped from online. So it was looking at chat rooms, online forums, and so on. The problem with that chatbot is that it started coming up with hate speech and responses to people interacting with it that were really just not acceptable. And obviously, this is not really come as a surprise when you think that it was actually trained on the content from the internet, which isn't exactly. There's some dark corners of the internet there, but it goes to show that without an understanding of the data that these systems are built on and the quality of that data, things can very quickly go wrong. Obviously, Microsoft very quickly took down that chatbot. Another example is bias in the data. So on the right here, we see an old example from Google Translate, where if you wrote, "he is a nurse, she is a doctor," and asked it to translate that to Hungarian, it translates that into Hungarian, which I've no idea what that actually means in Hungarian. I can't read Hungarian, but if you took that and then retranslated it into English, it actually changes over the gender here. So it changes to "she is a nurse, he is a doctor." So this is an example of how there's bias in the training data that these types of AI systems are trained on, and then that those biases are brought forward in the outputs of these systems. So then with these three challenges, we move on to talking about blockchain. So we've talked about data quantity, the quality of it, and the accessibility. But the question here is, so what really has this got to do with blockchain? So one of the aspects of blockchain and distributed ledger technology is fundamentally, it's about trust and validity of shared data. So the technical solutions behind this are quite complex how they actually achieve this. We often think of this in terms of digital cryptocurrencies, Bitcoin, for example. But the fundamental reason and ability of what blockchain can solve is trust and validity of the data. And we can explain this through the double spending problem. So this is really the motivation for digital cryptocurrencies and the original use case for blockchain, which is with Bitcoin, for example. So if we think of a physical asset, so in this case, it's a piece of cheese, there's some value in that. Now, Tom gives that asset to Jerry here. There's no double spending with this exchange of this asset. So that cheese, Jerry has that. Tom cannot give that same piece of cheese to someone else. It can't be double spent. And that's where we think of physical assets, physical money, and so on. But if we think about digital assets, then if we have a crypto coin, if we have a piece of software, anything that has value but it's in a purely digital form, the cost and difficulty in copying that is basically zero for a lot of digital assets. So we can easily copy a piece of software. We can copy the unique key of a digital coin, for example. So what stops Tom giving that to Jerry, and that's all good, and then he has a copy of that, he can take a copy of that and start giving it to other people. So suddenly the value of that asset can't be maintained. So the traditional solution to this is with centralized authority, a centralized digital asset. So for example, you could have a centralized bank where that keeps a record of who has which asset. And the key thing here is all the participants trust that central authority to maintain that single ledger that everyone trusts. And this solves the double spending problem for things like for digital assets. However, this means that this central authority, such as a central bank, has to be trusted by all participants. So it requires a high level of trust. Now, the participants themselves don't have to trust each other. They all just have to trust this central authority. Now, there's many situations and systems where trust of a central authority from a huge amount of participants is not really feasible. So if we come along to then blockchain and distributed ledger technology, this solves that aspect. So the way blockchain works is that each individual participant has a copy of that centralized ledger. Now, the underlying technology ensures that that copy is the same. Every participant has the same copy of that ledger. And furthermore, they can assure and be confident that their copy is the same as everyone else's. And everyone can validate whether someone's version of that distributed ledger is correct. So it's like a single version of truth, although that information is just fully distributed. And furthermore, there's no central authority that is managing this validity of the data across the network. And what this enables is digital assets and cryptocurrencies and digital coins, for example, can be exchanged. And if there's any duplication of that, everyone will know, everyone can discover that, and it stops the double spending problem. So often people think of, well, blockchain, maybe it's just a distributed database. It's just these different participants, they have a copy of the data, and it's just like a database distributed among many entities. But there's a subtle difference here. So on the left, we see this is what a distributed database looks like in terms of trust of that data. So with these type of databases, all the entities holding a copy of that data, they have to still trust each other. So there's no underlying technology or approach in classical distributed databases to make sure that one entity isn't maliciously changing the copy of the data that they hold on their own node. They might, if they don't trust each other, maybe one person can manipulate the data that they have. So there is this trust boundary around the distributed database itself. Whereas in a distributed blockchain ledger, we see where the trust boundaries here are distributed, and each individuals don't necessarily have to have full trust with each other. The underlying network, the underlying blockchain technology, and I'm not going to go into the complexities of how that works, but that ensures that each copy of the data is the same and can be verified, even though one of those entities could try and manipulate that data because there's not necessarily full trust between them. So to go back to the key features then of blockchain and distributed ledger technology, there's this trust that we just talked about. So participants, they don't have to trust each other in order to trust the validity and integrity of the data that they all see and they all share. The data integrity, well, every node can be certain that the data that they have is correct, as in it's the current version that everyone sees, and it's the same as everyone else's copy. So this provides a single version of truth of the data. So rather than each participant having their own copy of the data that they might have changed in certain ways, and that might be slightly different, the underlying technology ensures that the data that everyone sees is the same and everyone can trust that. And there's no central authority managing that. The immutability, so data that's put on a blockchain, that's stored on a blockchain, it cannot subsequently be modified once written to the ledger. You can make updates to it, but that history of what's changed in the data is complete, and everyone can inspect and view that. And that gives additional security and trust in that data. Data ownership and privacy. So blockchain isn't like a free-for-all on data where everyone puts the data out and everyone else can see it, and it's just sharing all this valuable and private data that an individual entity might have. Participants can still control who has access to their own data through cryptographic security. So they can still control within the blockchain whether anyone can see that data or anyone else can read that data. Security. So blockchains are typically very secure and difficult to hack. So for example, Bitcoin blockchain that's the oldest blockchain, and it's never successfully been hacked. And as you can imagine, there's a huge there'll be a huge desire to hack this. It's highly valuable. I mean, if you can steal Bitcoin or hack the network in some way, there's a huge financial reward to doing this. And I'm sure many people have tried, but the technology is very robust and secure. And smart contracts. So in addition to storing static data in a distributed ledger or blockchain, you can also store code. So this code can represent different kinds of functionality or a contract. And this can be shared and executed on the distributed ledger itself. Now, this is not just, for example, taking that data and manipulating that in some way and then writing that back to the distributed ledger. This is some code which represents a certain way of processing that data or certain actions, like a contract, for example, and that all the participants can see exactly what that code does. They can see any changes made to the code, just in the same way as the data in the blockchain can be shared and validated between these entities that might necessarily trust each other. And this can also be used for like automatic validation of the data that's been written to the blockchain or the format of the data and so on, which is has relevance to AI, AI and machine learning, which I'll talk to in a minute. So there's a huge, I'll go on to explain and talk about a project where we're using blockchain in supply chains and how then that powers and enables more AI approaches and machine learning and predictive analytics in the supply chain. So firstly, there's huge potential for AI in supply chains. So you can think of better demand prediction with predictive modeling across the supply chain. You can look at efficiency improvements by applying AI solutions in various aspects across that supply chain. Automated decision making. There's a lot of decisions made in supply chains which are very manual currently. If you can use potential AI solutions to make those decisions automatically, you could increase efficiency and reduce the sort of manual effort and time savings and costs in complicated supply chains. And also a lot of the automation of manual processing tasks associated with that as well. However, this is a kind of current view of what a lot of supply chains look like currently. So we see these different entities or participants. We have component manufacturers, subcomponent manufacturers. We have right up to the end customers, resellers, distributors. There's all these different entities doing very specific tasks and specific functions across this distributed supply chain. But the data is incredibly siloed within each of these individual entities. There's very limited data sharing. An entity would typically just share data with an immediate connection that it needs to do business with. There's no complete end-to-end view of such a supply chain. And we also have very diverse data formats. So every entity has data in its own format. They're not necessarily sharing that throughout the whole supply chain. And we have this difficulty in the validity of the data. But if we look at how a blockchain-based shared data model for supply chains can look, we see that with a blockchain data model, we have various entities again, but they're all operating on a shared blockchain. So it's a blockchain-based distributed ledger. And the key thing about this is not requiring a trusted third party. So in many examples of supply chain examples, to get all these diverse different entities that are required in a complex supply chain to put their trust in a third party that's going to manage the whole supply chain, collect all the data from each participant, perform the AI and analysis on this data and the security of that data and so on, that trust just isn't there to have a third party to do this. But with a blockchain model, each party can share the data to a distributed shared ledger, shared data model, but not necessarily trusting a third party that's going to have full control of this. And the key thing here then is entities, they're still able to own and control their own data, but they can benefit from sharing it. So in the shared data model view, the different entities, they're not necessarily sharing all the data that they have. They're choosing which other participants can get access to this data on that they need to know on a need to know basis. And going back to those three aspects of data that we identified as challenges in AI adoption. So in the quantity, well, with a solution such as this, there's much more data available across the full supply chain. And the data can be aggregated from these different participants. The data quality, well, a shared data model, it ensures much more consistency than these individual siloed approaches. And it provides a single source of truth of the supply chain data. Smart contracts can also be used to validate the data written to the blockchain. So this can ensure that there's consistent quality and that the data written to the blockchain conforms to certain formats and standards that through a governance model, all the supply chain participants can agree to. And the accessibility, well, the participants, they can still control which data they share and who can get access to that data. But AI solutions then can be built that have access to a full end-to-end view of the supply chain data. And it's, I suppose, there's a sort of individual entities here can see a benefit where if they're sharing their data to a provider that will, for example, provide demand prediction modeling on that data, that's a benefit to that individual entity. So they are more likely to be happy to share that data to fulfill those aims. And we're currently working on a project funded under the Disruptive Technologies Innovation Fund with companies Exertis, who's a supply chain service management company, and Sona Lake, which is a development partner on this project. And this is particularly looking at blockchain solutions for the technology product supply chain, which has many of those issues that I've highlighted here: really complex supply chains, siloed data, and currently the ability to apply AI solutions across these supply chains just really is non-existent due to these data problems that I've talked about. But it's not just blockchain isn't just a sort of drop in and everything's great solution. There's a lot of downsides to it as well. So this ability to share data and validate data across many entities that don't necessarily trust each other comes at a high computational overhead. So there's a huge amount of background processing of that data to ensure that everyone can trust that data. And that's a huge overhead that this lack of trust sort of brings to what's required. So it's not a replacement for a database technology. So to think of a blockchain just as a distributed database, well, we saw that in terms of how the trust works is slightly different, but also in terms of just as a mechanism to store data, this is not the case. So many blockchain implementations actually they try not to, the best approach is not to store large amounts of data on the blockchain, but to store the very specific valuable data, and also data that points to other data off-chain, but in a way that off-chain data can then be validated through the signatures and the IDs, for example, that are stored on the chain. You have to still trust the correctness of the data being written onto the blockchain. So what the data actually means and represents is obviously outside the scope of the underlying blockchain technology. So if bad data is being written onto the blockchain and it's not being checked, be corrected, then that data will still exist on the blockchain. So it can't do anything against actually the correctness of the data itself. And also the third aspect here is a limitation. It really needs buy-in from all the participants. And this is a challenge in many blockchain applications. And I think one of the reasons why there's been a huge buzz around blockchain and distributed ledger technologies over maybe the last 5 years for sure. And blockchain is about 10 years old, where it started out really, but that was just in the cryptocurrency kind of use case. But applying this to different domains has been challenging because you need this buy-in. So all the participants need to agree. It can, there's a change in the fundamental systems and the way things, even the business processes and way a lot of organizations currently work with sort of central authorities to manage data and so on. And it's just this change means that a lot of these kind of solutions are taking a while to be deployed. Now, particularly the project that we're working on in applying blockchain to the technology supply chain is a particular case here where we're very focused on looking at how we can bring blockchain into certain aspects of the supply chain. It's not a rip and replace where we're saying to get rid of all existing processes and existing solutions. We're looking at where this can be put in gradually, and as the benefits are seen, this will can be expanded much more across all the different participants and systems on a supply chain. So just to conclude, so as we've seen, there's many challenges with the adoption of AI, and many of these, and the key ones, seem to be all related to data. So we're talking about the quantity of data, the quality of data, and the accessibility to that data. Blockchain and DLT, distributed ledger technology, it supports the trust and validity of shared data. That's key. It's key what it brings. And we can see that then AI can benefit from this trusted shared data models. So this single idea of single version of truth hugely supports AI solutions and the deployment of them. And this can be enabled through blockchain. So that's, I suppose, how we can take these two modern technologies and we can see how blockchain actually does have a role in AI. They're strongly related, and it's something that we're really looking at in CeADAR across a number of different areas. So thanks very much. And if anyone has any questions.
Oisin, Kevin Neary here. I have a quick question for you.
Hi, Kevin.
Hi, how are you? Blockchain as a service, is that the blockchain as a service solutions that come from companies like IBM and Microsoft, is that fundamental to every blockchain project, or is that just one alternative that you can use to build a blockchain technology?
Yeah, so some of those, those solutions that some of the big vendors are supplying. So I think you can see them as, hugely useful in terms of actually building the technology. So I see them along the lines of, we see sort of AI as a service, we see, cloud as a service, we see these various technology as a service offerings. The underlying, an underlying blockchain solution can be built kind of from scratch, from the underlying libraries, such as like the Hyperledger framework, for example, which is an open source project. But what these as a service solutions do, and these companies are providing, is a sort of abstraction layer over those underlying libraries with many tools and different solutions built on top of that to sort of make the deployment of these faster, to make the development of blockchain solutions faster, and then also hosting those solutions as well. So, for example, in the project that we're working on in the supply chain solution, we're very much looking at how these sort of third-party blockchain as a service offerings can help in the actual deployment then of the solution.
Okay, great. Thank you.